This lesson is going to cover thermodynamics as it is concerned with general chemistry, more specifically general chemistry 2. For general chemistry, there are a few parameters of thermodynamic quantities we're concerned with. While there are more, the three that we're going to focus on are Gibbs free energy, enthalpy, and entropy, represented delta G, delta H, and delta S for the change of those values, specifically the difference between products and reactants for each of those quantities. Delta G is simply the energy a chemical reaction has available to do work. Of the total internal energy a chemical reaction might have, perhaps only some of it is actually available to do any kind of meaningful work. And delta H is the enthalpy of a reaction, which is the transfer of energy as heat. Delta S represents the change in entropy. Essentially, how does the orientation and distribution of every atom, every molecule, how does that affect the amount of work that's actually available? And that's why these quantities combined can be represented in the above equation. The change in free energy of a chemical reaction is always equal to the change in that reaction's enthalpy minus the product of temperature times the change in entropy. Temperature in this case is in units of Kelvin, and delta H is usually in either joules or kilojoules, or if we talk about molar quantities, joules per mole or kilojoules per mole, units of energy or energy per mole amount. Entropy is always going to be in joules per Kelvin or kilojoules per Kelvin, or if we have a molar amount, then divide those by moles. So for this reason, delta G is always going to be in joules or kilojoules or some unit of energy per mole amount. Unless in engineering, then energy per gram amount is also seen. Entropy, another way of looking at that, is of the total amount of energy that could be usable from heat, there's a certain amount of energy not available to the system because of the distribution and orientation of all the molecules and or atoms. So that helps us give a correction of how much energy is actually fully available to use. Now, the following is true of any chemical reaction, no matter what. Delta G always equals delta H minus T delta S. Now, if we have some normal reaction of reactants to products, if delta G becomes some positive value, we call that a non-spontaneous chemical reaction, also called endergonic. That means that there's not enough energy inherent to that chemical reaction to occur on its own. Therefore, a certain amount of energy must be supplied at the start of that reaction to get it to move to the other side. So delta G, if it's positive, that's the amount of energy that has to be added to the chemical reaction in order for it to actually occur. If delta G is negative, then that reaction in the direction where delta G is negative is spontaneous or exergonic. That means that that chemical reaction has enough energy already to go into the direction where delta G is negative, and therefore our value of delta G is actually the amount of free energy that becomes available to use elsewhere, or the amount of free energy released by that chemical reaction. And if delta G equals 0, or around near 0, that just means that our chemical reaction is at equilibrium. Therefore, both the forward and backwards reactions are happening in tandem with one another. So, just practicing this type of stuff. Let's say we have the following sets of information, and we're looking at the enthalpy of the forward direction, or delta G subscript F. Usually the F means formation. Here we're just looking at the forward direction from reactants to products. We have some chemical reaction where A decomposes into B and C. Based off of the first row of information, if we plug that into our equation, we should get a free energy change that is positive 2. By our second row of information, we should get delta G equaling 0. And the final bit of information, the final row, everything collapses into negative 30 kilojoules per mole. The important thing to know is, what conclusions can we make about the forward reaction? Well, at that particular temperature and those particular values of enthalpy and entropy, in the first row, we got a positive value. That means that in the forward direction, that reaction is non-spontaneous. It cannot occur on its own, and it needs 2 kilojoules per mole of energy added to it in order to go in the forward direction. Since delta G in the second row equals 0, the conclusion we can make is that the reaction is actually in equilibrium. So it's not just the forward direction that's occurring, but the backwards direction as well. And because the final row data, we had a negative value, we know that the reaction in the forward direction is actually spontaneous. It will occur on its own. If we just have A all by itself at a temperature of 5 Kelvin, then it will already have enough energy within itself to decompose and move in the forward direction to form B and C. The sign just means whether or not the chemical reaction can occur on its own, or if it needs some excess energy to be added. Positive means it's non-spontaneous. Negative delta G means it is spontaneous. Something fascinating, though, is that if we know the free energy change of our forward reaction, we also know the free energy change of our reverse or backwards reaction. So, from the following set of data, we calculate delta G to either be positive 2 under certain conditions, or 0 or negative 30. Here are the conclusions we can make from that. If free energy change in the forward reaction is positive 2, then in the reverse direction it would be negative 2 kilojoules per mole. If in the forward direction is 0, then in the backwards direction is also 0. And if in the forward direction is negative 30, then in the reverse direction, free energy change would be calculated as positive 30. Therefore, the conclusions we can make from the prior set of data is that when free energy change in the reverse direction is negative, then the reverse direction is spontaneous. That means that if we have B and C in the same proximity at the temperature where delta G equals negative 2, then they will automatically on their own progress towards A. They will go in the reverse direction without any help from us. If delta G equals 0, then again that just means we're at equilibrium. And if delta G in the reverse direction is positive 30, that means that at those given conditions, that chemical reaction will not move in the backwards direction unless we force it to by adding some excess energy or doing something that forces it to move backwards towards A. So in that case, the reverse direction, because it has a positive delta G, it would be non-spontaneous in the reverse direction specifically. Another way of looking at all this is really just if we look at free energy change equaling delta H minus T delta S, this chart just lets us know certain basic things. If we want a reaction to be non-spontaneous at all temperatures, then we need free energy change to be positive. Therefore, if we had free energy as some positive value and we had entropy as some negative value, then we would have some positive quantity minus a negative quantity, which would be overall positive. Therefore, free energy change is a chemical reaction will always be non-spontaneous if enthalpy is positive and entropy is negative, and it will not depend on temperature. If we want a chemical reaction to be spontaneous at all temperatures, then its enthalpy must be negative and its entropy must be positive. That way we have a negative value minus some positive quantity. Therefore, if for a given chemical system, if enthalpy is negative and entropy is positive, then it will be spontaneous in that direction for all given temperatures. And then if that's not the case, where enthalpy and entropy are both positive or they're both negative, then what actually matters is which one has a greater effect. And if the absolute magnitude of enthalpy is greater than the product of temperature and entropy, then that means that we would overall have some very large positive value minus a smaller positive value. Or we would have a very, very large negative value minus a very, very small negative value. Which in end means that if the reaction is spontaneous or non-spontaneous, it's enthalpy driven. If we have the situation where enthalpy and entropy have the same sign, they're both positive or both negative, but the magnitude of enthalpy is less than the magnitude of temperature times entropy, then that means that we would have a very small positive value minus a very large positive value, or we would have a very small negative value subtracted by a very, very large negative value, which in the end means that if free energy change is overall positive or negative, it will be predominantly entropy driven. That's the technicalities of all this chart here. Now, note 1, delta G depends only on the difference in free energy of products and reactants, or the final state and the initial state. It is independent of the path of transformation and is unaffected by the mechanism of reaction. That just goes into the fact that every thermodynamic parameter can also be called a state function. That just means it doesn't matter if it takes us 3 steps to go from reactants to final products. It doesn't matter if we do that chemical reaction in one single go, or if we have a bunch of intermediate steps in the way. For example, what if we had A going to B plus C in one step, or what if we had A decompose into some intermediate, maybe D, and then D composes into another intermediate, Z, and then Z breaks apart into B plus C. It doesn't matter if it takes us one step or many steps to go from our initial reactants to our final products. The overall value of delta G will still be the same regardless of how many steps it took. All that matters is what do we have at the end and what do we have at the start. Another way of looking at it is it doesn't matter if we take a straight line to go from point A to point B, or if we take some large curved path, or if we take a large zigzag and eventually move back from point A to point B. The path does not matter. All that matters is what's the free energy of our products and what's the free energy of our reactants. Therefore, delta G would be the difference of those two. Also, delta G cannot tell us about the rate of a reaction. There are 2 things that help drive a chemical reaction. There are kinetics and there are thermodynamics. Kinetics tells us the rate of a reaction, essentially how quickly will that reaction occur. Free energy does not tell us that. Free energy tells us, will a reaction occur on its own or will it not occur on its own? And if it can occur on its own, if delta G is negative, that doesn't mean that the reaction is quick. It might take milliseconds for that reaction to occur on its own. It might take minutes. It might take thousands of years. Delta G does not tell us if a reaction will occur quickly or slowly. It just tells us, will it occur on its own, or do we need to add energy to force it to occur? So, just like in a first semester general chemistry course where usually we look at the formation of enthalpy, we can look at the formations of Gibbs free energy like so. Determine the standard free energy change. Because this is standard, this will be delta G naught at 1 bar of pressure and 26.85 degrees Celsius for the following reaction. Essentially, there is some discrepancy between whether standard conditions are, say, 1 atmosphere and perhaps around 25 degrees Celsius, or sometimes it's considered 1 bar of pressure around 26.85 degrees Celsius. 1 bar and 1 atmosphere, they're around the same, 25, 26 degrees around the same temperature. Don't get too stuck on that. What matters is we're calculating the standard free energy change, which in this case is delta G naught. Well, let's do that for the following reaction. Ammonium nitrate as a solid, decomposing into its ions of ammonium ion and nitrate ion. Well, if we want to calculate delta G naught, let's first calculate the standard enthalpy and standard entropy. And all that is simply taking the sum of the enthalpies of formation for the products times their stoichiometry minus the sum of the enthalpies of formation for all the reactants times their respective stoichiometries. And then doing the same process for entropy, where we would sum up the entropies of formation of all the products multiplied by their stoichiometry minus the sum of the enthalpies of formation for all reactants multiplied by their stoichiometric coefficients. And then once we have those values, whatever temperature we're at, we'll have to convert it to Kelvin. Therefore, delta G naught equals the sum of standard enthalpy minus the product of temperature times the total standard entropy. And let's see. There we go. Now, if we have the following sets of enthalpies of formation and entropies of formation for all of our chemical species, here's how we plug all those values into the following. And what's not given is the units. That'll be on the next slide. Here's how we plug in everything. If we look at the enthalpy of formation, we have two products. We have ammonium ion, which has an enthalpy of formation of negative 132.5 kilojoules per mole. The stoichiometric coefficient is 1 here, so we'll multiply that by 1 mole of NH4+. Separately, we're now going to have the enthalpy of formation of the nitrate ion, negative 205 kilojoules per mole. And because of the stoichiometric coefficient, we'll also multiply that by 1 mole of nitrate. We'll then put all of that in its own set of parentheses. Off further, we're going to have all of our reactants. In this case, we only have one reactant, ammonium nitrate in the solid state, which in the solid phase, it would have an enthalpy of formation of negative 365.56 kilojoules per mole. Because the stoichiometry is 1 here, we'll multiply that by 1 mole of ammonium nitrate. And then we'll put that in its own parentheses. take the top set, add everything together, and then subtract it by everything in the second set. And if we do that, we end up getting 28.05 kilojoules per mole. Values of entropy tend to be very small. That's why we usually see them in joules per Kelvin or joules per mole Kelvin. We'll do the same exact thing that we did for enthalpy, but we'll do it for entropy, which the standard values for entropy of ammonia is 113.4 joules per mole Kelvin. And we'll multiply that by 1 mole of ammonium ion. We'll then add to that the product of 1 mole of nitrate times 146.4 joules per mole Kelvin. Put all of that in its own set of parentheses, and then at the bottom, we'll take 1 mole of ammonium nitrate times 151.08 joules per mole Kelvin. Since that's the only reactant we have, we'll put that in its own parentheses and take the difference between the top and the bottom, which ends up giving us 108.72 joules per Kelvin. Now then, the values we have are our standard enthalpy change from start to finish is going to be 28.05 kilojoules, and the standard entropy change would be 108.72 joules per Kelvin. Because we need our temperatures in Kelvin, temperature in Kelvin is just the temperature in Celsius plus 273.15. Therefore, we're told at the start that we're at 26.85 degrees Celsius. We'll add to that 273.15 to get a total temperature of 300 Kelvin. Now then, delta G would therefore be 28.05 kilojoules minus 300 Kelvin times 0.10872 kilojoules per Kelvin, essentially taking our entropy value, if it's in joules, dividing it by 1,000 to get it in kilojoules per Kelvin. And then that entire expression, the entire equation ends up equaling negative 4.566 kilojoules. Therefore, the reaction would be spontaneous in the forward direction if we're at 1 bar pressure and 300 Kelvin in temperature. We can also make the conclusion that in the reverse direction, from ammonium ion and nitrate ion towards ammonium nitrate, the free energy change would be non-spontaneous with a value of positive 4.566 kilojoules. And we care about the energy change per mole of reaction, then we could just say for every time we do 1 mole of reaction, we are going to have negative 4.566 kilojoules of energy expended. Nice thing about Hess's law, even though this is normally discussed when we just look at enthalpy, because every single parameter in thermodynamics, from free energy change to enthalpy change to entropy change, they're all state functions. It does not matter how many steps it takes to go from start to finish. So the same techniques we used for enthalpy way back, we can also use for free energy, as well as for calculating the entropy of a chemical reaction that might be very hard to calculate it in one step. But if we can do it through multiple steps with a known value of delta G, then we can calculate the free energy change of some other reaction of interest. Let's look at the free energy change of taking 2 moles of carbon monoxide gas with 1 mole of molecular hydrogen gas to form 2 moles of solid carbon and 1 mole of liquid hydrogen peroxide. Another thing to note is those free energy values, just like with enthalpy and entropy, they depend on the physical state of the substance. They can vary with temperature. That's why it's important to know the physical state of all of our chemical species whenever we're concerned with thermodynamics. Now then, let's say we have 2 known reactions. The reaction of carbon monoxide gas decomposing into solid carbon and half a mole of molecular oxygen gas has a free energy change of negative 237.1 kilojoules per mole. And then the free energy change of hydrogen peroxide liquid as it breaks apart into hydrogen gas and oxygen gas is going to equal positive 120.4 kilojoules per mole in the direction shown from reactants to products. If we can rearrange these chemical reactions in such a way that we end up getting our main reaction of interest, then we'll be able to apply Hess's law just like we did with enthalpy. Well, let's take the top reaction, or our top known reaction, where we have carbon monoxide gas. Well, if we look at our main reaction, carbon monoxide gas is a reactant. In this known reaction, carbon monoxide is also a reactant. So let's not change anything as far as what's a reactant and what's a product. But let's look further at the stoichiometry. Our chemical reaction wants to take into account 2 moles of carbon monoxide. This known reaction only takes into account of 1 mole of carbon monoxide gas. So in that case, if we want 2, let's multiply the entire chemical reaction by 2, so that we have 2 times carbon monoxide, and 2 times carbon, and 2 times 1/2 a mole of O2, giving us 2 moles of carbon monoxide gas, breaking down to form 2 moles of solid carbon, and 1 mole of molecular oxygen gas. For thermodynamics, if you multiply a known reaction by some multiplier, also multiply the free energy change by that number as well. Therefore, delta G, originally equaling negative 237.1 kilojoules per mole, we'll multiply it by 2 to get negative 474.2 kilojoules per mole. Now then, we have a subreaction that accounts for 2 moles of carbon monoxide. Nice. And incidentally, 2 moles of solid carbon in the product side. Check. Now let's look at our next subreaction. Well, our next subreaction has 1 mole of hydrogen peroxide in the liquid phase. Our main reaction of interest only wants to account for 1 mole of hydrogen peroxide in the liquid phase. So check. Let's not multiply this reaction by any number. However, in our known reaction, hydrogen peroxide is a reactant. We want it to be a product. So in this case, let's just take the reaction in the reverse direction. So instead, we'll take our products, hydrogen gas and oxygen gas, and make them reactants. And we'll take our hydrogen peroxide that was a reactant, and we'll now move it into the product side. If you make that change in a chemical reaction, well then, if our delta G was originally positive 120.4 kilojoules per mole, our modified reaction now has a delta G of negative 120.4 kilojoules per mole. While these two steps are not actually mutually exclusive, if you have to multiply a reaction or flip a reaction, you might have situations where you have to do both. Just know that if you have to multiply an entire known reaction by some number, multiply the free energy change by that number. If you have to flip a chemical reaction, also flip its sign. Now then, we have these numbers right here. Here's what's nice. If we were to run those two modified chemical reactions one right after the other, here's what we see. We have one reaction with a reactant of carbon monoxide gas and products of 2 moles of carbon and 1 mole of molecular oxygen. In our second subreaction, we have hydrogen gas as a reactant reacting with a mole of oxygen, molecular oxygen, to form hydrogen peroxide. So if we ran these two together, we effectively have 2 moles of carbon monoxide gas reacting with a single mole of molecular hydrogen gas to form 2 moles of solid carbon and 1 single mole of hydrogen peroxide. Because in one chemical reaction we produced O2 and in another reaction we consumed O2, and it was 1 mole that was produced and 1 mole that was consumed, effectively it's as if we can ignore them or cross them out. In reality, it's because the overall concentration of O2 doesn't change because we used some and we produced some. Therefore, we don't actually, it's not relevant to our overall chemical reaction when determining free energy. Because we can do this reaction and this reaction, one right after the other, to effectively equal our reaction of interest, to calculate delta G, we just need to add the free energy change of each prior step. Step 1 was negative 474.2. Step 2 was negative 120.4. Adding these two values together gets us a free energy change of negative 594.6 kilojoules per mole. Therefore, applying Hess's law, the free energy change of this main reaction is this value right here. Now, just some parameters of interest. Let's say we're looking at aqueous reactions. Technically, it's also true if we were looking at reactions with a gas. Let's say we have some chemical reaction where we have some equilibrium expression, some K constant. In a prior video, we were looking at concentrations, and each concentration of the products were raised to their stoichiometries, and each concentration of the reactants were raised to their stoichiometries, and these concentrations are for anything that's not in the solid phase, as well as not liquid water. So anything that's in the gas phase, anything that's in the aqueous phase, or anything that's a liquid other than liquid water, we would plug that into our equation here. Our gas constant, our universal gas constant, the value can change depending on the units. If we're in units of joules per mole Kelvin, that would be 8.314. Which if we want it to be in kilojoules per mole Kelvin, then that would be 0.008314. Here's how we can relate free energy change to our thermodynamic equilibrium constant. Free energy change equals the standard free energy change plus the product of RT natural log of K. If in this value right here we're plugging in K, then all this always equals 0. Because if we're at equilibrium and we're using our equilibrium constant, delta G of our reaction equals 0. Another way of using this chemical expression is if we had delta G equaling delta G naught plus the product of 2.303 times R times T times log base 10 of our equilibrium expression. This is just if you want to use log base E or natural log or log base 10. Otherwise, these are still going to be the same expression. And if we are in a situation where we're not at an equilibrium, we would instead use our reaction quotient. Therefore, delta G equals the standard free energy change of that reaction plus the product of the gas constant times temperature in Kelvin times the natural log of Q, or log base E of Q. Or we could just use delta G naught plus 2.303 times RT times the natural log, or times the log base 10 of our reaction quotient. It doesn't matter if you use this equation or this equation, they end up giving us the same values. And now, just as a little pre-introduction, we'll have a video on electrochemistry separately, but as a pre-introduction, there is such a thing as electrochemical equilibrium, where the change in voltage potential, or delta E, equals the change in voltage potential under standard conditions, delta E naught, minus the quantity RT over NF, the gas constant times the temperature, divided by the number of moles of electrons times Faraday's constant, all that multiplied by the natural log of a reaction quotient. And we can set that equal to delta G through the following expression. The free energy change of an electrochemical reaction is equal to the product of -1 times the moles of electrons being transferred from one side of our chemical equation to the other, times Faraday's constant, times the voltage potential. And if these were standard conditions, delta G naught equals negative NF times delta E naught. In any case, that concludes this little General Chemistry 2 video on what we need to know for thermodynamics. As always, likes and subscribes are not necessary, but they are appreciated, and perhaps this channel will get somewhere pretty cool. I'm hoping to pay for my Dunkin' drink someday with this YouTube money. In any case, glad to have you all. Thank you for watching this video to the end, if you did, and always a pleasure to have you all. And in conclusion, just around the 34, 36, 37 minute mark, glad to have everyone in the video. See you all in the next video. Peace.